Welcome back. We are continuing our discussion of the history of software-defined networks. Today we'll talk about network virtualization. We'll first talk about what network virtualization is and what it's useful for, and we'll trace its history back to the 1990s, as well as exploring some of the developments of network virtualization over the past 10 years in the form of both support for network experimentation as well as various concepts such as the separation of service providers from infrastructure providers that we saw in some earlier network architectures. We'll also look forward and talk about how network virtualization relates to software-defined networks. So to remind you where we are in the third of 3 lessons where we're discussing the evolution of supporting technologies. We just finished our discussion of the history of network programmability, and we also talked about the history of central network control. In this lesson, we will talk about the history of network virtualization. So first of all, what is network virtualization? Simply put, network virtualization is the representation of one or more logical network topologies on top of the same underlying physical infrastructure. And there are many different instantiations of network virtualization, some of them that predate even the 1990s, such as virtual LANs. What we're going to talk about in this lesson, however, are various technologies and network testbeds that used and developed network virtualization since then that have essentially led to some of the more mature virtual network technologies that we see in the form of companies and commercial products today. So first of all, what are the benefits of network virtualization? One of them is sharing. So using network virtualization, one can instantiate multiple logical routers on top of a single physical node or a single platform. And more generally, one can instantiate multiple virtual networks on top of the same physical network infrastructure. This sharing, of course, requires the ability to provide resource isolation in terms of CPU, memory, bandwidth, forwarding tables, and so forth. So in addition to sharing, network virtualization offers the prospect of customizability. Users of a virtual network could essentially get a view of their own logical network and logical network topology that's separate from other logical networks that may be running on the same underlying physical infrastructure. And the ability to see an independent logical network also allows the ability to run custom routing and forwarding software on that particular slice of the virtual network. So let's just look at what this might look like in terms of a few pictures. So let's assume we have a fixed physical infrastructure, and on top of that fixed physical infrastructure, the routers, links, and so forth, we might have multiple parties who want to use that fixed physical infrastructure. So we might have the red party and we might have the blue party, each of which might want access to different underlying physical network resources. Each of those parties might also want to instantiate different arbitrary virtual topologies on top of that underlying physical infrastructure. So the idea here is that each of these parties who wants to use the infrastructure has the ability to create their own view, or their own virtual topology, or own logical topology sitting on top of that physical infrastructure. And the idea is that each of these would be able to run independently without interfering with one another. So in the rest of this lesson, we will explore 3 different examples of virtual networks. One is the Tempest architecture, or switchlets, which dates back to the late 1990s. And some of the ideas that came out of switchlets are the separation of the control framework from the underlying switches themselves, as well as the ability or capability to virtualize the underlying switch hardware to provide the appearance of multiple virtual switches. The second virtual network technology that we'll look at is something called the Virtual Network Infrastructure, or VINI, which dates back to 2006, and the motivation here was to provide a virtual network infrastructure so that experimenters could run experiments with their own logical networks shared on the same underlying physical topology. Then we'll look at a network architecture called Cabo, which used some of the vision of the emerging virtual network technologies to realize that virtual networks could allow service providers to operate independently of the providers that make the underlying physical network infrastructure available. So let's first look at switchlets, which came out of something called the Tempest architecture. In this particular architecture, we have a single underlying switch with its resources, and then we have an open switch control interface that exposes those resources to software that's sitting above. Indeed, that control interface does look a little bit like OpenFlow. So the idea or the motivation behind switchlets was to allow multiple control architectures to operate over a single ATM network. The open control interface separated the switch controller and the fabric via an open signaling protocol, and the divider partitioned the switch resources to allow multiple controllers each to have their own view of a logical switch. Indeed, that looks a little bit like FlowVisor, something that we will explore a little bit more when we talk about modern SDN architectures, in particular OpenFlow. The switch divider partitioned port space, bandwidth, and buffers and allowed different controllers to control each switchlet. Now, in addition to the similarity of this architecture to some more modern SDN architectures, it's also interesting to note this paragraph in the conclusion of the paper that introduces the switchlet architecture. It says, as anyone can obtain a virtual network will effectively be a network operator, we hope to see an increase in the creativity that can be brought to bear upon the problem of network control. So that's interesting because it essentially predicts what happens next, which is the realization that virtual network infrastructures can allow network researchers to bridge the gap between small-scale experiments and simulation and real live deployments. And that was the motivation behind VINI, or the virtual network infrastructure. The idea here was that on one hand, we had controlled repeatable lab experiments that were potentially not so realistic, and on the other hand, we had live deployments which were very realistic, could scale up, run real traffic, but not necessarily be repeatable. And the idea here was that we could use network virtualization to bridge the gap between repeatability and realism. So VINI runs real routing software, exposes realistic network conditions to the applications running on it. It gives control to the experimenter over different network events, such as failures. It can carry traffic on behalf of real users. It can also be shared among many different experimenters. VINI also used a separation of the data and control planes to achieve some of its goals of network virtualization. Its control plane is a software router called ZORP, which runs a variety of different routing protocols with the goal of allowing the experimenter to run real routing protocols on top of virtual network topologies. VINI's data plane provides the appearance of these virtual network topologies to experimenters. VINI's data plane is implemented using a software router called CLIC, and the interfaces, the virtual interfaces, were implemented using a technology called tunneling, which is also used in many other virtual network technologies to create the appearance of virtual links. In VINI, experimenters could also put filters in front of these tunnels to create the illusion or appearance of failing a link. These filters would essentially just block packets on individual tunnels. Given the technologies to build virtual networks, researchers then began exploring how this technology could be used to facilitate the introduction of new services and speed the pace of innovation. One of those architectures was called CABO, or Concurrent Architectures Are Better Than One. This architecture offered the insight that the infrastructure providers, or those parties that maintained routers, links, data centers, and other physical infrastructure, could operate independently or separately from the service providers that offered end-to-end services on top of that infrastructure. Examples of this separation between infrastructure and service providers in some sense already existed. Two such examples were Packet Fabric, which allowed multiple ISPs to share the same physical routers at exchange points, and Phone, a commercial internet service provider that resells users' wireless internet connectivity to its customers. Phone has an interesting economic refactoring where the users in their homes who buy upstream connectivity from different internet service providers are effectively the infrastructure providers, and Phone is simply a broker of that internet service and effectively acts as the service provider. So let's just summarize what we've learned in this lesson. We have learned about network virtualization, in particular what it is. Network virtualization separates the logical network that users or service providers see from the underlying physical infrastructure and potentially allows multiple parties to share that same underlying physical infrastructure for different purposes. Network virtualization has a rich history dating back to virtual switches or switchlets in the 1990s, network testbeds such as VINI, and these architectures that envision using network virtualization to offer different types of services. The legacy of network virtualization for SDN is actually quite rich. The idea of separating service providers from infrastructure providers is something that we see a lot in commercial software-defined networks today. The idea of using multiple controllers to control a single switch and exposing multiple logical switches on top of a single switch is actually something that has roots in the switchlets architecture, and the notion that a single physical infrastructure could in fact expose multiple logical network topologies also has its roots in a lot of this network virtualization research. So to summarize, we've just completed 3 lessons that explore supporting technologies for software-defined networks. Next, we'll talk about different types of standardization of the control plane that were going on in parallel with the evolution of these supporting technologies.